Well, hello everyone. My name is Joel Coffman. I'm a technical lead at the Johns Hopkins University Applied Physics Laboratory. I work in a group focused on improving the security of OpenStack. And a little bit about the work that we have done. We've added features such as volume encryption, ephemeral storage encryption, and most recently we've done a lot of work with Barbican for secure key management within OpenStack. And so I'll be presenting about some of that work in this presentation. So since you all are part of this presentation, I assume that you will take it for granted that data is a very valuable commodity. People, not only cloud users, but also cloud operators, are very interested in protecting that data. And it's very important for the confidentiality of that data to be preserved, either due to regulatory compliance or simply as good business practice for many of the companies who are running public cloud offerings. So we want to protect that data both against accidental loss and various forms of unauthorized access. And this can be fairly difficult, especially when you have incidents like a disk failure, which may prevent normal data sanitization procedures from being followed. If you cannot write to the disk, the data may still reside on the platters even when the disk is disposed. And we want to make sure that we protect against those types of scenarios, as well as other concerns like multi-tenancy concerns that arise in a cloud computing environment. So not only do we need to protect the underlying data storage, we also need to make sure that we protect the data transmission that occurs within the cloud. And this is particularly important because typically for an OpenStack installation, it is assumed that the control network is trusted. In other words, all of the data is being transmitted in the clear, especially between the various block storage services that exist. And so we want to make sure that we protect that data as well. So some of the threats that we're protecting against are listed at the top of the slide: data not being securely erased, improper hard drive disposal, or physical security compromise are some of the ones that I didn't mention previously. So in order to combat some of these concerns and some of these threats to confidentiality, we have looked at adding several new security features to OpenStack, including ephemeral storage encryption and encryption for persistent volumes, or Cinder as the block storage service. However, it's fairly easy to know that the best encryption scheme without secure key management doesn't do us much good. And so in the Juno development cycle, we have also stepped up and increased our efforts to partner with the Barbican team to provide secure key management for OpenStack. So if you're not familiar with Barbican, Barbican provides a REST API, which provides access control to secrets. It is very general. Secrets could be encryption keys. They could be certificates. They could even be as general as passwords or passphrases that users want to protect. And our work within Barbican has specifically focused on adding a new abstraction layer to Barbican, which we've named the secret store abstraction. And the secret store abstraction is important because it generalizes the retrieval and storage of secrets. So this is a common intermediary or an interface that allows us to talk to different Barbican pluggable backends seamlessly. There are several different implementations. We have worked exclusively on a KMIP implementation. KMIP stands for the Key Management Interoperability Protocol, which is an OASIS standard for key management or for interacting with hardware appliances for key management. But there are several other implementations as well. There is a Barbican HSM, which has been developed by Rackspace. There is also a DogTag plugin, which has been developed by Red Hat. Now, our work for interacting with a KMIP server was actually spearheaded by another development effort in the creation of an open source library named PyKMIP. PyKMIP provides a general way to interact with KMIP hardware appliances. And so Barbican talks to the PyKMIP library, which actually translates all of the information necessary into the binary format that is required for interacting according to the KMIP standard. And we've released that. We have also tested the common operations that we have developed for Barbican, and we have tested all of those against various hardware appliances that have been supplied by hardware vendors to guarantee that it works correctly. So a brief walkthrough of how some of these features work together. Let's start with how everything works in the unencrypted sense. We start with compute host. We're going to launch a virtual machine instance. So we're going to take storage on the compute host, and we're going to make that available as ephemeral storage to the virtual machine. And that ephemeral storage is typically going to be backed by either a disk partition on the compute host or some kind of backing file, like a QCOW2 file. If we have a persistent volume, then we're going to have an external storage host. We're going to create an iSCSI connection to that external host from the compute host, and then we're going to make this new volume available to the virtual machine instance. So our work with the encrypted storage has focused on adding a de-encrypt style or de-encrypt layer between the privileged domain of the compute host and the virtual machine instance. And this is basically intercepts all of the calls so that everything is transparently encrypted and decrypted without the user's direct interaction. So we have Barbican stood up for key management in the cloud. And so the first thing we do when we're booting a new virtual machine instance that is going to be encrypted is we're going to start by fetching a key from Barbican. That key is going to be passed to de-encrypt. And once that key is in de-encrypt, it is going to be used to transparently encrypt and decrypt all of the ephemeral storage. Similarly, if we have a storage host, then we're going to fetch the key from Barbican, we're going to create the iSCSI connection, and then we're going to pass the encrypted storage up to the virtual machine instance. All of this is transparent to the end user, so they will know that they are interacting with an encrypted virtual machine or encrypted persistent volume. However, it requires no direct interaction on their part. It is also important to note that this architecture that we have designed is beneficial in that it also provides protection for the data in motion for sender volumes, because the iSCSI connection, instead of transmitting the bits in the clear, it's actually transmitting encrypted bits. So if an attacker has access to the network backbone, they could essentially reconstruct an encrypted version of the disk. However, they would not have access to the underlying data stored in that disk. So how does all of this work in practice? Let's take a walk through setting up all of these options from both the administrator and the end user's perspective. So the first key piece from the demo video is actually creating an encrypted volume type. Cinder has volume type abstractions, which represent a certain class of volumes, and it's an abstraction already within Cinder, independent of our work. So we're going to start by creating a volume type codenamed Lux, and then once we've created that volume, which has already gone on, we're going to use that volume and make it an encrypted volume. And all we're going to specify here is we're going to specify an encryption provider, which identifies how to connect the de-encrypt style mapping within Nova. And then we're going to specify a cipher, mode of operation, and a key size. And that's the extent of the administrator's involvement in configuring an encrypted volume type. For an end user to actually use these features, we've integrated them with the dashboard, so it is very easy to use. We are assuming in this case that an administrator has also pre-configured the compute host in order to make all of the ephemeral storage on that host encrypted. And so when the user is actually going to launch a virtual machine, it is the same user interface that they are accustomed to. It's simply going to be encrypted without their direct interaction or involvement. So very straightforward. And typically what we envision is that an administrator would designate a certain pool or class of storage hosts to all be encrypted. For using encrypted volumes, again, the process is very seamless for the end user. They're going to create a new volume, and the only thing that they have to specify is that they're going to use an encrypted volume type. So here what you'll note is that it's going to specify Lux as the volume type, which is the encrypted volume type that we created just a minute ago. And then all of the encryption metadata, the cipher, key size, all of that is going to be associated with the volume for future reference when we're using the volume. In order to attach the volume to the instance, again, it's the same process that end users are accustomed to. They're going to simply click Attach to Instance, and then they're going to designate the encryption or the instance that they booted previously. And you'll notice that there is also a new encrypted column with the volume in the Horizon dashboard that identifies that the volume is encrypted. Now, if we peel back the covers and actually write some data to the volume and show what's being written behind the scenes. We'll start by logging in to the encrypted virtual machine instance. We're going to echo the string hello world to a file. Then we're just going to sync that file to make sure that it is written to the underlying compute storage. And once we've done that, that's the extent of what we're going to show for the demo purposes. Similarly, if we're writing to an encrypted volume, the end user is going to log into the instance. They're going to write some text directly to the underlying storage device. This is not typically how an end user would interact with backing storage. However, it is very illustrative for the sake of the demo. You'll note there at the very top of the screen that hello world does appear in the storage device. Now, what happens if someone else were to gain shell access to to either the compute host or to the backing storage host? What you can see in the demo is that all of the bits in the ephemeral storage have been encrypted, so it looks like random nonsense to the end user who did have shell access. Similarly, if we log in and look at the contents of the encrypted volume, here what you're going to notice that there is a LUX header. So it starts with LUX, and then you can see some of the encryption metadata, such as the cipher and the key size, which appear at the very beginning of the volume. All of this follows the full disk encryption standard, which is used already within Linux. And so that is the only parts that a administrator or someone who did have shell access would be able to see without the encryption key. So really, to summarize the work that our team at APL has been doing for the past couple of years, we have been focused on data encryption. Rackspace did a survey a couple years ago in which they asked their customers what are the most important data protection features that could be added to OpenStack. And far and away, the result that they found was data encryption was the most highly sought after feature. So independent of that knowledge, we were actually embarking on providing data encryption for OpenStack. And we've done so, as I showed in the demos just a minute ago. Now, one of the questions that we always get is what's the performance penalty? What we have found is that it does add some additional overhead. However, typically it's about 10%, which we believe is very reasonable for most workloads. And in fact, if you have a more realistic network setup where the storage host and compute host are decoupled for persistent volumes, it's probably going to be less than 10% due to the latency of the network. Brief timeline of the work that we've done. The Havana release added volume encryption. We laid all of the groundwork for ephemeral storage encryption in the Icehouse release. We completed and provided ephemeral storage encryption for the LVM backend in the Juno release. We've also stepped up our efforts to provide secure key management in OpenStack. And we're also pursuing much more extensive dashboard integration to make it much easier to use these features by the end user. In terms of future work and where we're headed, we're going to continue to support these features. We have additional patches for supporting things like backups of encrypted volumes within Cinder and additional dashboard integration. We also hope to provide confidentiality and integrity assurances for glance images so that there is a root of trust to guarantee that we are booting the correct image and we're booting it correctly. And then finally, we also hope to extend support, basically doing the same work that we have done, but putting it at a lower level in the stack, in this case QEMU, so that we can provide encryption across all the different backends that OpenStack could support, including backends like Ceph. So thank you very much for your time. And if anyone has any comments on the work that we are proposing, I'd love to hear feedback from you.